When you step outside into a winter storm, it is easy to assume the snow hitting your jacket is simply rain that froze because the air near the ground is cold. But that soft powder actually begins its life 5 miles above your head. The creation of a single flake is a highly fragile mechanical process. It starts with a piece of hardware. Snowflakes cannot materialize out of thin air. They require a physical seed to build upon, a speck of pollen, atmospheric dust, or even volcanic ash. This requirement is called nucleation. When water vapor in the upper atmosphere strikes this seed in sub-zero temperatures, it skips the liquid phase entirely. Through a process called deposition, the gas snaps directly into a solid ice shell. If the vapor turned into liquid water first, you would simply get a drop of standard ice. The vapor must bypass the liquid state completely for a crystalline structure to grow. As more water molecules lock into place, they are forced into a strict 6-sided shape. This hexagonal lattice is dictated entirely by the molecular geometry of H2O locking together. Every time a new water molecule bonds to the structure, it releases a tiny burst of energy called latent heat. This micro-warmth slightly raises the temperature immediately surrounding the crystal, creating a vapor gap that actively pulls in even more moisture. This continuous tug-of-war of atmospheric pressure forces the ice to build outward, eventually forming the classic, highly detailed branches of a stellar dendrite. What lands on your glove is a meticulously engineered structure, assembled molecule by molecule through precise, localized pressure dynamics. Building the crystal is only the first hurdle. The snowflake now faces a perilous 5-mile descent to the surface. To survive the drop, the entire vertical column of air must be freezing. If the snowflake hits extremely dry air, it sublimates, evaporating mid-air into virga. Alternatively, a warm inversion layer permanently melts the crystals into rain. Accumulation on the ground proves that an unbroken 5-mile-high chain of thermal and pressure conditions held perfectly intact. Sometimes, cities with mild, wet climates experience heavy snowfalls even when the thermometer reads above freezing. This happens through a mechanism called evaporative cooling. As the first flakes fall into dry air, they evaporate. That evaporation draws heat out of the surrounding environment, dropping the local temperature until it carves out a localized freezing tunnel for the rest of the storm to follow. Conversely, pure water droplets can fall without encountering a freezing seed, remaining completely liquid well below 0 degrees. When this supercooled water finally impacts a frozen object, it instantly snaps into thick, solid armor. The mid-atmosphere functions as an active, volatile filter. The specific path a droplet takes decides if a city gets soft powder, heavy slush, or destructive clear ice. When those crystals do manage to stick, their structure is mostly trapped air. This provides natural acoustic insulation that absorbs sound and a highly reflective surface that bounces solar energy back into space. So why do certain regions that sit at high altitudes and reach freezing temperatures fail to produce snow? Take the dense concrete skyline of São Paulo. When a cold polar mass hits this region, it is usually accompanied by high atmospheric pressure. That pressure forces air downward, violently pushing out the ambient moisture required to build clouds in the first place. Even if moisture returns and the vertical column aligns perfectly, the vast expanse of concrete and asphalt creates an urban heat island. The city stores solar radiation, projecting a final thermal shield that melts incoming crystals on contact. Invisible pressure systems above and artificial human infrastructure below work in tandem to block the final stage of the snowflake's journey. As global baseline temperatures rise, you might expect snow to disappear entirely. But a warmer planet is actively engineering heavier, more intense snowstorms. This graph charts global air temperature against moisture capacity, demonstrating the Clausius-Clapeyron law. It shows a sharp exponential upward curve. For every degree the atmosphere warms, its capacity to hold water vapor expands drastically. When that supercharged moisture payload finally collides with an intact, freezing vertical column, it dumps massive, concentrated amounts of physical weight onto the surface. The delicate 5-mile requirements for snow will align less frequently, but the blizzards that do survive the gauntlet will carry more water and strike with more force than they ever have before.